Hello, higher physicists, and today we're going to have a look at the 2017 multiple choice questions from section 1 of the higher physics paper. And without any further ado, let's make a start. Question number 1, it says the graph shows how the velocity of an object varies with time. The acceleration of the object is... So, what can we see from this graph? Well, we can see the change in velocity over the time, which is what acceleration is. So A equals V minus U over T is the formula to use. Final speed is 10. Initial speed is 5 over a time of, well, from 2 to 8 seconds is 6 seconds. So that is 0.83 meters per second, or answer A. Question 2. A block is resting on a horizontal surface. A force of 24 newtons is now applied as shown, and the block slides along the surface. The mass of the block is 20 kilograms. The acceleration of the block is 0.2 meters per second. The force of friction acting on the block is... So, that 24 newtons is being applied at some angle of 60 degrees to the horizontal. So, that can be broken down into two forces, an upward force and a horizontal force. Now, that forms a right-angled triangle. The block is going to move horizontally, so it's the horizontal component of the force that we're going to be interested in. So, the horizontal force forms the adjacent side of that triangle. So, if we think about SQA, cos is adjacent over hypotenuse. Or, as I sometimes try and remember, if I'm going across the angle, it's a cos for a cross. So, whichever way, it's all to do with cos. The friction acts in the opposite direction. So, that horizontal force, 24 cos 60, which is 12 newtons. So, there's 12 newtons pulling this block forward. There is an acceleration of 0.2 meters per second. So, the unbalanced force from Newton's second law equals ma. 20 times 0.2 is 4 newtons. If that's the unbalanced force, that tells us there are 4 more newtons pulling in one direction than in the other. So the frictional force must be 4 newtons less than the 12 newtons that's pulling it forward. Therefore, 12 minus 4 equals 8 newtons. Answer B. Number 3. The graph shows how the vertical speed of a skydiver varies with time. The student uses information from the graph to make the following statements. Firstly, the acceleration of the skydiver is greatest between P and Q. No. Between P and Q, we can see the speed is constant. Therefore, the acceleration would be nothing. 2. The air resistance acting on the skydiver between Q and R is less than the weight of the skydiver. Well, between Q and R, you can see his speed is decreasing. Therefore, the force of air resistance must be greater than his weight in order to be slowing him down. And finally, 3, the forces that on the skydiver are balanced between R and S. Well, between R and S, we can see that it's moving at a constant speed. Newton's first law says if the forces on an object are balanced, it will remain at rest or continue with a constant speed. So therefore, constant speed, balanced forces. 3 is true. So the answer is 3 only, answer C. Number 4. A spacecraft is traveling at a constant speed of 2.75 times 10 to the power of 8 meters per second relative to a planet. A technician on the spacecraft measures the length of the spacecraft as 125 meters. An observer on the planet measures the length of the spacecraft as... So, length contraction, L dash equals L times the square root of 1 minus V squared over C squared. People get confused about which letter is L dash and which is L. So, in this case, L dash, the dash one, is always the one seen by an observer moving relative to the object. So L dash is what we're trying to find out here, because the observer is moving relative to the spacecraft. So L dash equals 125 times the square root of 1 minus v squared over c squared, as it is there, which turns out to be 50 meters. Answer B. Number 5. The galaxy has a recessional velocity of 0.3 c. Hubble's law predicts that the distance between Earth and this galaxy is... So, Hubble's law, V equals HOD. V is 0.3 times the speed of light, so 0.3 times 3 times 10 to the power of 8. HO is Hubble's constant, which we can get from the data sheet. So just rearrange that, and we get a value of 3.9 times 10 to the power of 25 meters. Answer B. Number 6. Measurements of the expansion rate of the universe lead to the conclusion that the rate of the expansion is increasing. Present theory proposes that this is due to dark energy. Number 7. A student makes the following statements about the radiation emitted by stellar objects. Stellar objects emit radiation over a wide range of frequencies. That is true. The peak wavelength of radiation is longer for hotter objects than for cooler objects. That is false. The hotter the object, the shorter the peak wavelength will become. So cooler objects tend to be more towards the red end of the spectrum, hotter objects more towards the short wavelength blue end of the spectrum. 3. At all frequencies, hotter objects emit more radiation per unit of surface area per unit of time than cooler objects. That is true. The hotter they are, the more radiation they're going to be giving off. So 1 and 3 are correct. Answer D. Number 8. The following statement represents a nuclear reaction. Nucleus Z is... So what we need to remember is that both the atomic number and the nuclear mass number need to be the same on both sides of the arrow. So in this case, the atomic number is 103 and the nuclear mass number is 256. Therefore, the total on the right-hand side needs to also be 103 and 256. So, on the right-hand side, there is something plus the alpha particle, the helium nucleus. So, Z must have 256 minus 4 for its nuclear mass number and 103 minus 2 for its atomic number, which gives us a value of 252 and 101. Now, element number 101, if we find our periodic table and look for 101, we'll see it's that one, mendelevium. So Z must be mendelevium, MD, and the numbers are 252 and 101, which gives us answer A. Number 9. Radiation is incident on a clean zinc plate, causing photoelectrons to be emitted. The source of radiation is replaced with one emitting radiation of a higher frequency. The incidence of the radiation, irradiance of the radiation incident on the plate remains unchanged. Which row in the table shows the effect of this change on the maximum kinetic energy of a photoelectron and the number of photoelectrons emitted per second? So, kinetic energy first of all. Well, the incoming photons are now more energetic because they have a higher frequency. Okay, the equation E equals HF tells us that. The higher the frequency, the more energy the incoming photons have. If the incoming photons have more energy, then therefore the electrons that they cause to emit will also have more energy because more energy will be transferred to them. Now, number of photoelectrons emitted per second, well, that has to do with the number of photons that are hitting the surface per second. And as it says in the question, the irradiance of the radiation incident on the plate remains unchanged. if there is no change to the irradiance of the incoming light, then there are the same number of photons hitting the zinc plate. Therefore, the same number of electrons will be emitted. So we're looking for an increase in the kinetic energy, but no change to the number of photoelectrons emitted. Answer C. Number 10. Ultraviolet radiation of frequency 7.7 times 10 to the 14 Hz is incident on the surface of a metal. Photoelectrons are emitted from the surface of the metal. The maximum kinetic energy of an emitted photoelectron is 2.67 times 10 to the minus 19 joules. The work function of the metal is... So, this formula is in our formula sheet. Kinetic energy of the emitted photoelectron equals HF minus HFO. HF is the energy of the incoming photon. HFO is the work function of the metal. So, HFO is what we're trying to calculate. Let's put the numbers into this formula and work it out. So, we know the kinetic energy, we know Planck's constant, H, and we know we know F, rather, which is 7.7 times 10 to the 14. So, a little bit of rearranging here. Minus FO is going to be 2.67 times 10 to the minus 19 minus 6.63 times 10 to the minus 34 times 7.7 times 10 to the 14. So, HFO, the work function of the metal, is going to be 2.44 times 10 to the power of minus 19 joules, or answer B. Number 11. A student makes the following statements about waves from coherent sources. Waves from coherent sources have the same velocity. True. Waves from coherent sources have the same wavelength. True. Waves from coherent sources have a constant phase relationship. True. 1, 2, and 3. Answer E. Number 12. A ray of red light passes from a liquid to a transparent solid. The solid and the liquid have the same refractive index for this light. Which row in the table shows what happens to the speed and wavelength of the light as it passes from the liquid into the solid? So, the important statement here is that the solid and liquid have the same refractive index. If they have the same refractive index, that means they have the same effect on the light. Therefore, the light will not speed up nor slow down as it moves from one material to another. Therefore, no change. Answer E. Number 13. A ray of blue light passes from air into a transparent block as shown. The speed of this light in the block is... So, we've got light obviously changing direction when it goes from one material to another. That means it will slow down as it enters the block. However, what speed does it actually go to? Well, this formula in our formula sheet, sine theta 1 over sine theta 2 equals lambda 1 over lambda 2 equals v1 over v2. We don't know anything about the wavelength, so we'll ignore that bit, and we'll just use sine theta 1 over sine theta 2 equals v1 over v2. Theta 1 and v1 are the angle and the speed in air. Theta 2 and v2 are the angle and the speed in the material. So let's put those numbers in, remembering to measure our angles between the ray and the normal. Now, we're trying to work out V2, which at the moment is at the bottom of this fraction. I always find it far, far easier to work out the number when it's on the top. So let's flip the whole thing the other way up and multiply the speed of light across to the other side. And we get a value of 2.23 times 10 to the power of 8 meters per second, which is answer D. Number 14. A student carries out an experiment to investigate how irradiance varies with distance. A small lamp is placed at a distance d away from a light meter. The irradiance I at this distance is displayed on the meter. This measurement is repeated for a range of different distances. The student uses these results to produce the graph shown. The graph indicates there is a systematic uncertainty in this experiment. Which of the following would be most likely to reduce the systematic uncertainty in this experiment? Well, why is there a systematic uncertainty, first of all? Well, if we look at this, this shows that 1 over d squared is not 0 where the irradiance is 0, or the irradiance isn't 0 when 1 over d squared is 0. That means there must be some ambient background light getting into the detector. So even when you are effectively at a distance of an infinity from this source, there is still some light reaching it. So the light that is entering the detector is not just due to the source that we're investigating. We would expect usually a line a bit like that. So this is due to the background light level. So if we could repeat the experiment in a darkened room, answer D, then that would eliminate that effect of there being background light and therefore improve the reliability of this experiment. Number 15. A point source of light is 8 meters from the surface. The irradiance due to the point source at the surface is 50 milliwatts per square meter. The point source is now moved to a distance of 12 meters from the surface. The irradiance due to the point source at the surface is now, okay, inverse square law, I equals k over d squared, which means the irradiance from a particular point source is equal to some constant divided by d squared. If we rearrange that, we get this. Irradiance multiplied by d squared is always equal to some constant. We can therefore write the formula like this. I1 d1 squared equals I2 d2 squared, which means the irradiance multiplied by the square of the distance at one place will be equal to the irradiance multiplied by the square of the distance at any other place. In this case, I1 is 50 milliwatts per square meter, and D1 is 8 meters. D2 is 12 meters. So we can insert those numbers into the formula, change things about a little bit, and we get a value for I2 of 22.2 milliwatts per square meter, which is answer A. Number 16. The output from an AC power supply is connected to an oscilloscope. The trace seen on the oscilloscope screen is shown. The Y gain setting on the oscilloscope is 1 volt per division. The RMS voltage of the power supply is. So from the oscilloscope, we can get the peak voltage. That is the amplitude of the voltage signal. We can see that the amplitude is 3 boxes at 1 volt per box. So the peak voltage is 3 times 1, which is 3 volts. To convert a peak voltage to an RMS voltage, we divide by the square root of 2. So 3 divided by root 2 is 2.12 volts. Answer A. Number 17. A 20 microfarad capacitor is connected to a 12 volt DC supply. The maximum charge stored on the capacitor is. So we have the supply voltage, we have the capacitance of the capacitor, so we can just use C equals Q over V, or Q equals CV, to find the charge. Capacitance, 20 times 10 to the power of minus 6 times 12 volts, gives us 2.4 times 10 to the power of minus 4 coulombs. Answer B. Number 18. A circuit containing a capacitor is set up as shown. The supply has negligible internal resistance. The maximum energy stored in the capacitor is. So, quite a lot to do here for your 1 mark. First thing we need to realize, that's our supply voltage there, 6 volts. But this is set up as a potential divider. There are 2 resistors, R1 and R2. And therefore that supply voltage will be split between these 2 resistors, V1 and V2. V1 and V2 together would have to add up to 6 volts. The R1 is the resistor that's going to control the capacitor. So the maximum voltage that the capacitor can have across it is the voltage that R1 can have across it. Therefore, we need to find out, first of all, what is the voltage across R1 in this potential divider. So, use this formula. V1 equals R1 over R1 plus R2 times Vs. We put our numbers into the formula and get a value of 1.2 volts. So the voltage across the capacitor when it's fully charged is going to be 1.2 volts. Now we have this formula, E equals a half QV equals a half CV squared equals a half Q squared over C. We don't know anything about charge, so the first and last of those formulas are no use to us. We have to use the middle one, E equals a half CV squared. So we multiply a half by the capacitance of the capacitor, 30 times 10 to the minus 6, times 1.2 squared, which is 2.2 times 10 to the power minus 5 joules. Answer E. Number 19. A student makes the following statements about conductors, insulators, and semiconductors. Firstly, in conductors, the conduction band is completely filled with electrons. That's not true. In a conductor, the valence band has electrons in it. It just so happens that the bottom of the conduction band and the top of the valence band somewhat overlap, but the conduction band is not filled with electrons. 2. In insulators, the gap between the valence band and the conduction band is large. That's true. In an insulator, it's very difficult for an electron in the valence band to have enough energy to jump that very large gap, move into the conduction band, and hence it does not conduct well at all. And lastly, in semiconductors, increasing the temperature increases the conductivity. That is true. Increasing the temperature causes the electrons to move more quickly, have more energy, and therefore be more likely to move into the conduction band, and therefore more likely to conduct. So increasing the temperature increases the conductivity. So 2 and 3 are correct. Answer E. And the final question, astronomers use the following relationship to determine the distance d to a star. For a particular star, the following measurements are recorded. Apparent brightness, F, 4.4 times 10 to the minus 10 watts per square meter. Luminosity, L, 6.1 times 10 to the power 30 watts. Based on this information, the distance to the star is... Okay, all we have to do is put the numbers we're given into this formula. So there's our formula. Put those numbers in. F we know, L we know. We want to work out D. So we get to that point. So 4 pi squared d squared, so 4 pi d squared rather, is going to be 6.1 times 10 to the power 30 divided by 4.4 times 10 to the power minus 10, which is 1.38636, and so on. D is going to be the square root of that divided by 4 pi, which is 3.3 times 10 to the power of 19 meters, which is answer A. Okay, folks, I hope that was helpful to you. That is all of the questions from the 2017 multiple choice section 1 paper of the higher physics exam. Hope it was useful, and I'll talk to you again another time.